Modern operating systems strictly require multiple continuous streams of data to constantly compete for shared physical computing infrastructure. These processes all fight for access to strictly limited resources, like specific blocks of memory, database row locks, and network interfaces. The standard lifecycle for these resources is simple. A process requests access, utilizes the component to execute its task, and then immediately releases it for others to use. But occasionally, competing processes find themselves permanently stuck, waiting for resources that are actively held by one another. This terminal state is known strictly as a deadlock. When this catastrophic event happens, the affected processes freeze entirely in place, and overall system throughput instantly drops to absolute zero. In modern system architecture, this represents a total cessation of progress, requiring rigid engineering frameworks to prevent system collapse. It is common to think of deadlocks as random glitches or unpredictable software bugs, but they are actually highly specific mathematical states governed by 4 exact prerequisites, known as the Coffman Conditions. These 4 conditions operate as a strict logical AND gate. Every single condition must be present simultaneously for a deadlock to exist. To see exactly what structural flaws are required to halt a system, we will engineer a deadlock from scratch. Defining the Coffman conditions transforms a system freeze into a measurable, preventable engineering state. This animated diagram is a resource allocation graph. Process 1 is a circle, and resource 1 a square, with process 2 and resource 2 adjacent. An assignment edge indicates resource 1 is actively assigned to process 1, and resource 2 to process 2. In this current configuration, the system is perfectly stable, and normal throughput is maintained. To push this toward failure, we need the first of the Coffman prerequisites, mutual exclusion. Mutual exclusion dictates that at least one resource is completely non-shareable, locked down so only one process can use it at a time. Hardware components like printer spoolers operate this way. So do strict database write locks, where allowing parallel access would corrupt the data. While locking these resources guarantees data integrity during concurrent execution, it also establishes the structural bottleneck required for a system failure. With our non-shareable resources established, we introduce the next requirement. Condition 2 is hold and wait. Returning to our diagram, process 1 now actively requests a new resource, resource 2. Notice that process 1 refuses to release its current hold on resource 1. A safer allocation policy might force a process to drop all current resources before making new requests. However, complex calculations often require reading multiple datasets or controlling several hardware components simultaneously to complete a task. Therefore, hold and wait is an operational necessity. It locks existing system components into idle states while creating active, unfulfilled demand elsewhere, tightening the system's flexibility. Operating systems generally possess broad authority to manage process priority and schedule execution, but Condition 3 limits that authority: no preemption. Under no preemption, the operating system is strictly forbidden from forcefully stripping a resource away from a process. The connection cannot be severed from the outside. The resource can only be released voluntarily by the specific process holding it, and only after its task is complete. The architectural reasoning here is simple. Interrupting a mid-process memory write to reallocate that memory block would lead to data corruption. We now have non-shareable resources, held indefinitely during new requests, with unbreakable allocations. No preemption removes the operating system's emergency override switch. The system must rely entirely on the individual processes to resolve their own wait states. Even with these 3 strict conditions in place, the system will not crash until a final geometric shape is formed. Condition 4 is circular wait. Let's execute the final move in our graph. Process 2 requests resource 1, permanently closing the dependency loop. This vulnerability scales up. In real-world servers, this forms massive chains of dependencies across multiple processes. Resolution is now mathematically impossible. Every process is waiting on the node directly in front of it to voluntarily release a resource. System throughput has now hit absolute zero. This completed, inescapable loop is the defining state of a deadlock. Circular wait connects isolated wait states into a terminal ring, structurally guaranteeing that no individual process can ever proceed, freezing the entire architecture. When diagnosing real-world system failures, software engineers often conflate two distinct problems. It is assumed that deadlock and a state called starvation are the same failure state. This split-screen diagram illustrates the difference. Starvation is an issue of priority. On the right, a high-priority process continuously cuts in line to grab a central resource, forcing a low-priority process to wait indefinitely. The underlying geometries are entirely different. Deadlock is a closed cyclic dependency. Starvation is a linear throughput inequality. Starvation is a localized fairness issue where overall system progress continues. Deadlock is a systemic structural failure that guarantees zero progress. We began by establishing that the four Coffman conditions operate as a mandatory logical AND gate. Because all four conditions must exist simultaneously, shattering just one condition automatically restores system execution. Deadlocks are mathematically predictable. By architecting systems to explicitly prohibit just one Coffman condition, developers can guarantee continuous operation in complex, multi-threaded cloud environments.